Our senses flood us with sights, sounds, smells, tastes, and feelings. They allow us to experience the world around us. Without our senses, that world would disappear. Without our senses, we'd be completely lost. Although our senses are crucial to our survival, we still know very little about them. But now, there's a revolution going on. A new breed of scientists are attempting to unlock the secrets of our senses. To do that, they're using bizarre and unorthodox methods to trick our brain into revealing how our senses really function. Does what you see affect what you feel? Does the sound of a food change its taste? Can we smell danger? I'm Jennifer Gardy. My mission? Discover how scientists are rewriting our understanding of the senses by putting these questions to the test and finding out whether they're myth or science.
How wrong was I?
Sight connects us to the world like no other sense. Color, movement, even emotions are all communicated to our brain by what we see. Sight guides us, protects us, and provides us with our richest experiences.
So it's not surprising that sight is the sense we trust the most.
Given that, it seems to make sense that seeing is believing.
But is that myth or science?
To find out, I'm heading to one of the oldest magic shops in London.
Watch this.
Magicians are masters at manipulating what we see. Gustav the Great is no exception. By night, he's a magician. But by day, Gustav Kuhn is a professor of psychology at Goldsmiths University of London. His specialty is the science of magic and illusion, a field that he believes holds the key to understanding how our senses work, especially our sense of sight.
I'm very excited about visual illusions and the way that we can trick the brain, because that provides us with really interesting insights into visual cognition. Magicians over thousands of years have really learned how to manipulate what people see, what they remember, and how they reason about the world. And it's only really been quite recently that scientists have started to study some of these techniques more scientifically.
To get to the bottom of whether or not seeing is believing, Gustav needs to find out how I'll respond to a simple illusion.
Oh, let's do that one again. I'm not a very good juggler. Okay, Jen, watch.
Okay. What happened to the ball?
My brain fell for this trick for a simple but critical reason. There's about 1/10 of a second delay between the information being received by our eye and processed by the brain.
Now, 1/10 of a second doesn't sound like a lot, but it means that in order for me to do this, and not this, ow, my brain has to predict what's going to happen next.
And that's exactly what it did when I watched Gustav's illusion. He threw the ball into the air twice, then palmed it. I was fooled because my brain expected the ball to go up into the air. So that's what I saw. In turn, this made me believe the ball had disappeared. Psychologists like Gustav call these expectations our internal model. It's the way we see the world, and it's based on our life experiences. My reaction revealed that my brain didn't rely on what it saw, It depended on the internal model to predict what would happen next.
Our perception of the world depends on what we attend to, so what we're interested in, but also based on our expectations. So you actually perceive the world the way that you expect the world to be.
Myth busted. Even though our sense of sight has been refined over millions of years, we still can't believe everything that we see.
If seeing really isn't believing, what does that mean for one of the most spectacular things we set our eyes on? Color. Seems pretty obvious that with colors, what you see is what you get.
But is that myth or science? Turns out it's a myth. Take a look at this checkerboard here. We've got squares of two different shades, and clearly this square is lighter than this square. Or is it? Check this out. If I slide the lighter square up, suddenly it's the same shade as the darker square. Check it out again. Lighter, darker. Why does this happen? Well, it has everything to do with context.
This cube of colored squares reveals just how context affects our perception of color. This square appears brown, and this one orange. But look what happens when you take away the context of the other colored squares. They're exactly the same.
So although it seems color is a fundamental property of an object, the reality is it's all in our head.
Color is at the forefront of the research of Charles Spence, a neuroscientist at Oxford University. His main area of expertise is our sense of taste, and he believes there may be a link between taste and color.
So here's a claim: the color of a drink can affect its taste. Myth or science?
Charles has designed an experiment he hopes will help him find out.
So I think it's time to do a little bit of a taste test. Very colourful taste test, in fact.
Excellent.
Just to see how people's brains combine what they see with what they taste.
Let's go.
We're setting up our taste testing booth at the Gloucester Green Market in the heart of Oxford.
And this is our setup?
That's it. So if you'd like to take a bottle
Okay.
and get pouring.
You've got what
Looks like a purple.
Yeah, like a grape, maybe.
Or maybe not. We've got a number of unique drinks ready for our taste testers. Charles has changed all of them so the flavors don't match the colors. First up, a cherry-flavored drink that's been colored purple.
One of these.
Thank you. And it's non-alcoholic, is it?
Non-alcoholic, sadly.
Sadly. Oh, that's nice.
By putting the senses of taste and sight into conflict, Charles hopes to better understand how taste works.
And what flavour would you say it was?
Sort of mulberry?
Mulberry. Ah, down in one.
I think it's blackberry. Blueberry.
Blueberry?
Tastes like blackcurrant.
Blackcurrant.
Some
Okay.
sort of
The
berry.
fact people keep naming flavors according to how the drink looks is intriguing to Charles.
So would you surprised if that's really cherry?
Really? That's actually quite surprising.
Next is an apple-flavored drink that's been colored orange.
That's more like tangerine.
Tangerine, okay.
Tangerine, okay.
Yeah.
Oh, it's apple juice.
Can I try that one again?
Yes, absolutely.
She doesn't believe us. She doesn't
No, I
believe us.
don't. I drink a lot of apple juice, fresh apple juice.
Yeah.
So. Yeah. How wrong was I?
It's an extremely simple experiment, but the results are far-reaching. Charles has discovered that the brain relies on our internal model when it comes to taste. In this case, a lifetime of associating orange flavor with orange colors causes us to believe a drink tastes like orange, even when it's got an apple flavor.
This one
Yes.
is apple.
Really?
Yeah.
I think an experiment like the colour drink study that we ran demonstrates just how multisensory our perception is. and how what we think we're experiencing via one sense, what we think we're tasting the drink in a cup, is really the result of integration of many senses to give us the experiences, say, of taste and flavor that we know and love.
Claim proven. The color of a drink affects how we perceive its taste. In essence, we're tasting with our eyes as much as we are our mouths.
Building on his finding that sight plays an important role in taste, Charles Spence wants to discover if it's possible that other senses also influence taste.
It's an interesting idea that leads to another unusual claim. How our food tastes can depend on how it sounds. Myth or science?
To find out, I'm heading over to Charles's lab at Oxford University.
You'd like to come this way?
Absolutely.
And I'm going to get you to sit in the soundproof booth in here.
Okay,
Okay?
all set.
Charles specially created this booth to study an area that's been difficult to understand, the interplay between taste and
Would you
sound.
like to put the headphones on?
Sure.
It's my job to rate the chips, 1 if they're really stale, and 100 if they're nice and crisp.
Cheers.
And Charles has designed it so I can only hear myself chew through headphones.
It seems fairly fresh. I'd say, gosh, maybe 85 out of 100.
85? Okay.
Like taste and sight, Charles believes that taste and hearing may be connected.
It's not particularly fresh, maybe like 55 or so.
We're all done. Thank you.
That was good. Can I have more?
Of course, there was far more to this experiment than meets the eye. Or make that the ear. Every chip Charles gave me was fresh out of the bag. So why did I rate them so differently? Turns out he was manipulating what I was hearing.
When you were biting into the potato chip, I had systematically been reducing those high-frequency crunching sounds that you normally associate with crisper, fresher foods.
Ah, so it was feeding back right away.
So you're hearing the sound of a stale chip while eating a fresh one.
Pretty sneaky. Charles also made the sounds more crispy.
Interesting.
And then for the last one, I ramped up all those high-frequency sounds. The traditional view was that we have 5 senses: sight, hearing, smell, touch, and taste. There's a kind of a visual brain, there's an auditory brain, a smell bit of the brain. And that view has become radically overhauled of late as more of these multisensory interactions come to the fore.
In the chip experiment, one set of information comes from my sense of taste and another from my sense of hearing. Both enter the brain where the taste of the chips is moderated by the sound they make when I bite into them.
Clearly up here, the senses are talking to each other, communicating, and one is influencing another. Brain is kind of all the time trying to combine the senses to deliver sort of optimal percepts about what's really out there in the world around us.
Claim proven. How a food sounds does affect its taste. Even more far-reaching, our senses don't operate alone. They work closely together. Coming up, I go to Germany to discover if we can smell danger. And what's in a name? Does what something's called affect how it smells? We smell with every breath we take. Although we're surrounded by scents, usually they only come to our attention when they're particularly wonderful. Or downright nasty. Our sense of smell is extremely powerful, but is it capable of helping us survive? When it comes to avoiding danger, most of us think about using our eyes and ears, even our fists. But using our sense of smell? Not so much. Sure, our noses can tell us when there's a gas leak or rotten leftovers, but do our olfactory alarm bells go off when we face a human threat?
Most people would say that it's impossible for us to smell danger, but is that myth or science.
To sort this one out, I've come to Germany to meet Smiljana Mutek. She's part of a neuroscience team at University Hospital in Aachen. Smiljana wants to discover whether chemical signals produced in sweat during boxing can subliminally alert us to trouble.
I'm going to ask you to hit the punching bag as hard and as fast as you can for 3 minutes.
She's recruited a group of volunteers to study these chemosignals, which have no overt smell. Many animals use them to signal danger. Smiljana wants to determine if humans can do that too.
Ready, set, sweat.
To find out, she needs to get sweat from volunteers as they do something really aggressive. The guys are all wearing shirts with special cotton pads sewn into the underarm. When they're good and sweaty, it's time for the gloves and the shirts to come off.
Got it. And they're placing them in so that, again, we're not introducing any of our own odors?
Yes, that's right.
Okay, notice that one.
To get a baseline, Smiljana is also collecting sweat from the guys as they do a movement similar to boxing, but minus the aggression. With our samples in hand, we head to Smiljana's lab.
Gloves.
You can take scissors and we will cut out the pads.
There we go.
All right, please take a seat.
Now comes the challenging part. Smiljana has recruited a new group of volunteers who have no idea what they'll be sniffing.
It's a natural low-intensity odor.
Their job is to help her find out if the aggressive chemosignals from the boxing samples can be detected.
Do a reaction time.
First, each person will smell a pad with non-aggressive exercise sweat. At the same time, they take a special reaction time test. It involves identifying the colors of anxiety-related words, such as violence, as quickly as possible. Each reaction is timed to the millisecond. Next, the volunteer repeats the test, but with the aggressive sweat. Smiljana is watching to see if the reaction times change. If the volunteer is slower while smelling the aggressive sweat, it will reveal that he's paying more attention to the words on the screen and is therefore sensing the danger.
So, walk me through the results.
We can see that when our sniffers were smelling aggression chemosignals, it took them longer to respond to anxiety-related words compared to exercise chemosignals.
Interesting. So when they're smelling the sweat from the boxers, they've got a slower reaction time. Why is that? I mean, it seems counterintuitive. It seems that when you're confronted with danger, you would respond quickly, kind of fight or flight style.
Yes, but in this case, it was a freeze response. They were stopping to evaluate the odor and the word, and it took them longer because the odor might be potentially important.
So essentially, the brain, when confronted with a threatening odor, it pauses. It takes time to process that, to really assess the threat.
That's right.
So in a sense, we can literally smell danger.
Yes, we can.
Researchers believe that humans lost the ability to communicate using the sense of smell long ago. But now, Smiljana and her team have shown that even subliminal aggressive chemosignals can be picked up by our noses.
Claim proven. Even if you don't realize it, your nose and brain are always on high alert. Keeping you safe. I could smell that one coming.
There's no two ways about it. Hockey gear smells foul. You know that once these players are off the ice, everything from their jerseys to their socks will have an odor that will make your toes curl. Yeah, these guys will tell you they're nose blind. They can't smell a thing. So, is it true that we can get used to a bad smell?
Turns out we can, and it happens rather quickly. It's just another way our sense of smell has evolved to protect us.
When the smell of sweaty equipment wafts through your nose, it hits your olfactory bulbs and then makes its way to the limbic system, which is associated with emotion and behavior. Here, your brain identifies the smell and reacts to it.
Once your brain's decided that a stinky locker room doesn't pose an immediate threat, it shuts your olfactory receptors down, often after just a couple of sniffs. This ensures your brain is ready to perceive the next odor it encounters, something that might be more dangerous.
Nose blindness reveals what a vital role our brain plays when it comes to smell. It decides right away if an odor is threatening or not. But is our sense of smell, like our sense of taste, also affected by those expectations we build up over a lifetime?
According to Shakespeare, that which we call a rose by any other name would smell as sweet. But is that true? Does what we call something affect how it smells?
Searching for an answer is a neuroscientist with one of the most finely tuned noses in the academic world. Johannes Fresnelli specializes in odor perception here at Sacré-Cœur Hospital in Montreal. Johannes has a library of hundreds of smells at his fingertips. Lavender, curry.
That is definitely licorice.
Using these, he wants to discover if what we name something affects how it smells.
First step is the olfactometer.
Yes.
Johannes will pump different odors into my mask and flash their names on the screen. I have to rate them from 1 to 9. 1 is horrible, 9 is very pleasant.
To make sure that you are not disturbed by any sounds.
Seems pretty straightforward, except Johannes has neglected to mention one key fact. He isn't always going to give me the correct name.
And if you're ready, we have a go.
Yeah, let's go.
Okay.
Let's smell.
Let's smell.
Excellent.
While I take the test, Johannes will be watching my responses on a monitor in the next room.
Okay, now we start the experiment. She will be getting the first odor in a couple of seconds.
Ooh, I like that. Oh, that's not too bad. This one's okay, but not fantastic.
So the next one is fresh flowers again, but she thinks that's a cheap perfume.
Ew, certainly wouldn't wear that.
All right, the next one is almond extract again, but it's coming with the label glue stick.
That one is quite unpleasant.
Okay, the next one is a good one. We're gonna give her Parmesan cheese again, but it comes with the label dried vomit.
Oh, that is disgusting.
The positive name.
Time to find out what the heck Johannes was up to.
So what we did in this experiment was actually we presented you odors under different names. Each odor was presented with a positive name and a negative name. So when it's Parmesan cheese, you rate it as mildly unpleasant.
It wasn't a great smell,
but
yeah.
Vomit, fresh, dried vomit, you actually rate it as very, very unpleasant.
Yeah.
I think the most striking one, you can see it here, where you have the response to the fresh cut flowers or to the cheap perfume. When it's flowers, you rate it as positive, it's pleasant. When it's the cheap perfume, you rate it as relatively unpleasant.
That's fascinating. It's exactly the same smell, but my brain interprets it as two completely different odors.
Johannes knows that I'm receiving information from the sense I smelled and from the words I saw on the screen. But there are very few direct connections between the areas in the brain where we perceive smell and the centers of speech where we handle language processing and comprehension. So, to define a smell, the brain turns to the other senses for help. In my case, it chose the information it got from the words I saw rather than from the scent I smelled.
This experiment shows us the importance of the context to perceive odors, to the odor perception. So if I perceive an odor in a context where I expect this odor to be pleasant, just the context will make the odor be more pleasant. And I think this is so amazing. So much information in every split second travels to our brain, and we integrate that and we make sense out of it. The sense of smell is a miracle.
Claim proven. How we label a scent affects how we perceive it. It's not just happening in here, but also up here.
Coming up, things take a turn for the bizarre as I try to discover if our sense of touch can trick us into accepting a rubber hand as our own. And we rig a university lecture to find out if just seeing creepy crawlies is enough to get people scratching. Touch is our most intimate sense. It has the power to convey even the most complex emotions. It's how we reassure, comfort, and show affection. We already know that when our senses work together, they can change our perception of the world. But is it also possible that the integration of touch and sight could be so powerful it could dictate how we perceive our own bodies? It's a question that intrigues cognitive neuroscientist LaDan Shams. She heads up the Multisensory Perception Lab at UCLA.
Hi, LaDan.
Hi.
So, here's a claim she and her team are examining. Working together, touch and sight can fool us into believing that an inanimate object is actually part of our body. To uncover if this is myth or science, LaDan is going to use a very unusual test.
So walk me through. What do we need for our experimental setup?
We'll need a table, 2 paintbrushes, a bib, a fork.
Wait a second. This is the weirdest experimental shopping list I've ever heard.
It gets weirder.
Only in LA.
So just follow my lead.
The rubber hand is key. LaDan's goal is to see if she can get a group of volunteers to feel like it belongs to them.
All right, now I'm just gonna ask you to scoot forward quite a bit.
Her grad student, Majid Samad, will be at the helm.
Great. And let me just, and maybe a little bit to the right. Great, now if you just let me position your left arm, please.
Majid places Mary's left arm behind a screen where she'll no longer be able to see it.
And now your right arm. All right, awesome.
LaDan and I will monitor a galvanic skin response sensor clipped to the finger of each volunteer. It measures how much they're sweating. Readings go up when the brain thinks the body is under threat. Now, the rubber hand is where Mary's left hand should be.
A little surprising? Yeah. Now please just observe what I do.
Majid begins stroking Mary's hidden left hand and the rubber hand simultaneously.
Does it feel like it's your hand?
100%.
Of course, there's really just one way to confirm that.
That's how.
Ooh,
There it
up.
goes.
That's it. That's a very big reaction.
That's a huge reaction.
Proof that, for a moment, Mary adopted the rubber hand as her own.
That's so crazy.
LaDan says a person who sees and feels the stroking has to weigh 2 possible scenarios.
One scenario is that the rubber hand is an object that doesn't belong to my body. An alternative scenario is that the rubber hand belongs to my body, and all the sensations that I'm processing and experiencing at this moment are stemming from this rubber hand.
So it feels completely like your hand at this moment?
No!
In a previous study, Ladan and Majid found that 80% of people felt the rubber hand was part of their bodies.
So if you were to look at this one and back at this one, you'd feel exactly the same?
Oh my god.
Were you frightened by that?
Yeah. I thought you stabbed me with a fork.
The reason we adopt this foreign object, a fake arm, as part of our own body is because of the relationship between the sensations, the information we get from our visual modality, information we get from our skin, the touch, and how they relate with each other induces us to believe that they are all coming from the same source. It is a compelling illusion in that the sensory information we receive completely changes the identity of ourselves, the bodies that we have lived all our lives.
But surely after seeing subject after subject get fooled, my brain would know what belongs and doesn't belong to my body.
That's weird.
Feels weird, doesn't it?
That looks very odd.
All right, so now just please observe what I do.
I've been watching this all afternoon, and it's fooling me.
So, so this feels like your hand as much as this feels like your
Yeah,
hand?
no, completely.
And so if I was to do this...
God!
Rubber hand illusion reveals that multisensory processing is key to sensation of self, our identity, our consciousness of who we are. And one would think this is something hardwired, we were born with it. But it turns out that evolution doesn't really hardwire things unless it's absolutely necessary. So evolution has decided that it's better to be adaptive and calculate the ownership of body rather than fix it and make it immutable. It's an ongoing process that we cannot really take for granted.
Claim proven. The rubber hand illusion is a perfect example of how our senses integrate to create our perception of reality. No matter how strange that reality might be.
Our skin plays a vital role when it comes to our sense of touch. It serves as a watertight barrier, protecting our insides against the dangers of the outside world. All over our skin, we have nerves that transmit information to our brain about what we're feeling. Scientists have discovered some of these nerves are dedicated to just one aspect of touch: itching.
If there's a set of nerves whose sole purpose is to tell us that we need to scratch, what about this claim? Just thinking about something itchy is enough to make you want to scratch. Myth or science?
This is the question that Donna Lloyd wants to answer. She's a cognitive psychologist at the University of Leeds and is fascinated by the powerful way sight and touch interact. But what she wants to uncover is whether one sense can actually create a physical sensation that doesn't even exist.
So, why can vision help us to feel the world? Well, it's because touch can interact with the other senses.
So to find out if just looking at something itchy is enough to get us scratching, Donna has rigged up a fake lecture.
Okay, what we call multisensory neurons.
Her audience believes we're there to film her, but we're actually interested in their reactions.
And it all begins for us with the feel.
During her lecture, Donna is going to slowly introduce photographs of insects crawling on people's skin to see if these will get the students scratching.
Multisensory system, amazing. I don't know if you've ever
Donna begins her experiment with neutral images.
So this is really our interest, if you like, is how these sensory systems can substitute for touch.
But she soon starts changing the photographs. The impact is immediate.
that are more near the surface of the skin, and we've got ones that respond to pressure. But the ones that we're particularly interested in are these ones here that respond to temperature and pain and itch.
Even Donna can't help herself.
And I'm going to invite Jen to come and ask you a few questions about your experience.
My cue to fess up.
So, as Donna mentioned, we were interested in your responses to the lecture, and we had our cameras turned on you. And what do you think we saw? There was a lot of itching in the audience, wasn't there?
It was kind of gradual, like the more pictures you were showing, the more it was like building up in me, and I was trying to resist it quite a lot.
When we see images of ants and bugs, this information is transmitted to the visual part of the brain. But it doesn't just go there. It's also directed to the areas that deal with touch. When it arrives, this visual information is transformed into a tactile sensation. These are the same areas activated when we're actually bitten by an insect.
What's really nice about our perceptual systems as well is that they will quite often do a little bit of second guessing on our part. So they get some ambiguous or not clear information from the sensory system, but they go, but this is what I predict is happening out there in the environment. The magic happens in the brain. That's where the real understanding of the world comes from. So even talking about itch, sorry.
Claim proven. Just thinking about an itch can get you scratching. And amazingly, what you see can determine what you feel, even when what you're feeling doesn't exist.
Bah.
Coming up, I head for Southern California and a researcher with a very strange way of finding out if you can believe everything you hear.
Bah.
Hearing is the sound of a Chopin etude. It's the rustling of leaves and the clamor of urban life. But perhaps most importantly, hearing is the heart of communication. But can we always trust our ears?
We've all heard the old adage that you can't believe everything that you hear, but have you ever wondered whether that's myth or science?
Larry Rosenblum is a specialist in visual and auditory perception who also enjoys laying down a few jazz riffs when he has the chance. Larry has a plan to help us figure out if we can believe everything we hear. But it isn't straightforward. Larry's discovered you often have to go to bizarre lengths to understand how the senses work.
What I'd like you to do is look at my face. It will be speaking, and it will be saying a syllable over and over again.
Okay.
I just want you to tell me what syllable you hear.
I can do that.
Ba. Ba.
Ba,
Ba.
ba. You're saying ba, like Baba Black Sheep.
Exactly correct. Okay. I'd like you to do it again.
Okay.
But this will be a different syllable.
Mhm.
And just, again, tell me what you hear.
Okay.
Ba. Ba.
This time you're
Ba.
saying va, va, with a V.
Yeah. That's what most people say. Ba.
But that's not what's being said. According to Larry, both sounds are exactly the same. Both are ba with a B. Check it out for yourself.
Ba. 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 Ba.
You're hearing va, 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 right?
Ba.
Okay, close your eyes.
Ba. Ba. Ba.
Now it's ba, 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 isn't it?
Ba. Ba.
Open your eyes.
Ba. Ba. Ba.
Wild, eh? This time, Larry places the two videos side by side. Take a look at the one on the right first.
Ba. Ba. Ba.
Now the one on the left.
Ba. Ba. Ba.
Again, the audio is exactly the same in both. This phenomenon is called the McGurk Effect.
Ba. Well, your ears are getting ba over and over again. What your eyes are getting is va. And what's happening in your brain is the visual information is actually going to the audio part of your brain and affecting what you believe you hear. It goes right to the auditory primary cortex.
That is so strange. The part of my brain that should be just hearing is hearing and seeing at the same time.
That's exactly right.
In the McGurk Effect, ba comes through our ears and va through our eyes. Because the brain is so desperate for information, it's not really picky about which sense provides the data. Forced to choose quickly, it goes with the information that's most dominant and selects va from our sense of sight. And we hear a sound that doesn't even exist. It's this kind of anomaly that scientists like Larry Rosenblum try to uncover because they reveal how our senses create our perception of the world.
It's really terrific that the brain is able to do this sophisticated detecting and integration of information without us, having to be bogged down by having to think about it, right? I mean, it's an automatic process that just seems to give us the information we need to know what we're perceiving in the world.
Claim proven. Thanks to the McGurk Effect, it's clear that you can't believe everything that you hear.
Our senses are remarkable. They connect us to the outside world through complex interactions that happen deep inside the brain. This multisensory web of sights, sounds, smells, tastes, and feelings can be interpreted in millions of ways. But incredibly, just one reality emerges, a noisy, beautiful, and rich world of sensations. To achieve this extraordinary feat, our senses need each other. Together, they have the power to create magic, the extraordinary symphony that is our perception of the world around us.